Okay, my atomic friends, I'm going to show you something that relates to my entire life. I started in physics when I was very young, and when I was in the Army, I was in nuclear missiles, servicing the missile sites and so forth. And I continued on. I had a business in electronics, and I believe I have the new theory of that replaces the standard model. The standard model doesn't work. Even this guy, Richard Feynman, he said that you cannot justify quantum mechanics with the standard model. It doesn't work. And he's right. And he said it doesn't matter how beautiful your theory is, it doesn't matter how smart you are, if it doesn't agree with the experiments, it's wrong. And that's correct. I'll show you the experiments, and they show dipole electron flood theory is a valid theory that should at least be examined. Let's take a look. All right, this is Feynman. He was a multifaceted American theoretical physicist and Nobel laureate. He made groundbreaking contributions to quantum mechanics, quantum electrodynamics, and all that stuff. And he was an honest guy. And he said, I really don't understand it. He said, I don't understand it. I'm trying to figure it out, but I don't understand it. All right, this is from an article that was done in 2010 and updated in 2013, quantum field theory, and they're talking about Feynman and what his problems were with the standard model. Well, it just didn't work. And the basic, all you have to do is go to here. It says Feynman argued the standard model is inconsistent and incomplete. It just doesn't work. And nobody could figure it out. And this is extremely detailed, and it goes on and on and on. I got to be honest with you. I only read to a certain point, but I mean, this is the Casimir effect of field to field. You see this? When you go field to field, it pushes back. And that's what we had in our experiments. And Feynman was all about experiments. He said, if you can't see it and prove it with an experiment, it's just a theory. It means nothing. And he goes on and on and on and on and on and on and on. And the videos are not available, which they just terminated his videos. Anyway, that's Feynman. Okay, I went to virtually every school online that I could find that was offering things for free, which is Yale has quantum. This is free. This is Professor Shankar. I just wanted to see what he had to say. And right in the first minute, in 1 minute, I understood what he's going to have to say. It was meaningless. He's a nice guy. He's just being honest. And he's talking about Feynman. Listen to what he has to say.
Bad news and good news. The bad news is that it's a subject that's kind of hard to follow intuitively. And the good news is that nobody can follow it intuitively. Richard Feynman, one of the big figures in physics, used to say no one understands quantum mechanics. So in some sense the pressure is off for you guys, because I don't get it and you don't get it and Feynman doesn't get it. The point is, here's my goal. Right now I am the only one who doesn't understand quantum mechanics. In about 7 days, all of you will be unable to understand quantum mechanics. Then you can go back and spread your ignorance everywhere else. That's the only legacy a teacher can want. So,
he's a nice guy. He's just being honest. He doesn't understand it. Feynman didn't understand. He just said it doesn't make sense. It doesn't work with the standard model. We got to come up with something else. And then he went to assault his peers for Nazi-like attacks on any new information, which they did, and he was quite outspoken. And anyway, he was right. They just will not let you speak. If you don't say what they want you to say, you can't speak. And just like he said, I'm going to tell you what to say. You say it, everybody will think you're smart. All right, this is Feynman, and he's talking about light, and not only light, but all the vibrations in the spectrum that are in the air, and all of these different things. And they were broadcasting radio waves, and at another place they'd pick them up and they'd see whatever they were broadcasting. So somehow they had to be able to isolate those waves from every other wave. And how many other waves are there? Listen to what he has to say. I'm going to put captions on so you can read it. He's saying there was information coming from Moscow radio being broadcast. Let me go back a little bit. All right. He's talking about in the space that we're in right now. There's all kinds of different frequencies of everything. Now we got all kind of wireless everything, and it picks up all that information. How does it do that? And I'm still a little bit wondering. Now listen to what he has to say.
You get longer and longer, and you're all through the same space. All these things are going on at the same time, so that in this space there's not only my vision of you, but information from Moscow radio that's being broadcast at the present moment, and the seeing of somebody from Peru. All the radio waves are just the same kind of waves, only longer waves. And there's the radar from the airplane, which is looking at the ground to figure out where it is, which is coming through this room at the same time. Plus the X-rays, cosmic rays, and all these other things, which are the same kind of waves, exactly the same waves, but shorter, faster, or longer, slower. It's exactly the same thing. So this big field, this area of irregular motions of this electric field, this vibration, contains this tremendous information, and it's all really there. That's what gets you. If you don't believe it, then you pick a piece of wire and connect it to a box. And in the wire, the electrons will be pushed back and forth by this electric field, sloshing just at the right speed for a certain kind of long ways. And you turn some knobs on the box to get the sloshing just right, and you hear Radio Moscow. But you know that it was there. How else did it get there? It was there all the time. It's only when you turn on the radio that you notice it. But that all these things are going through the room at the same time, which everybody knows. But you got to stop and think about it to really get the pleasure about the complexity, the inconceivable nature of nature.
I like this guy. Unfortunately, he died in 1988. But he was ahead of his time, and he said it just doesn't work. This quantum stuff and a standard model, it just doesn't work. Standard model couldn't account for gravity, couldn't account for dark matter, for matter. It couldn't account for a bazillion different things. Dipole electron flood theory covers all of that, and I can't find any inconsistencies with anything. So if anybody does have one, I'd like to hear it. I was working on Feynman and dipole electron flood theory and showing that Feynman was one of the biggest big shots in physics, and he says the physics doesn't work. The quantum mechanic model just doesn't work with the standard model. It can't work. And I have dipole electron flood theory, and not a single thing doesn't work in my theory. I can show it. And he was really elegant because he was in physics as a big hotshot physics guy, but he said no, it doesn't work. And they gave him the Nobel Prize, I don't know exactly, for something to do with physics. But he was able to stand up to all these guys and say, no, your model doesn't work. And if you can't show it and demonstrate it, it's a theory that just has no substance. And that was the case. They had no substance because they couldn't show anything. And all they had was flowery, fluffy things. Now they're talking about the universe having a memory. Who's going to prove that? The universe has a memory. And there's all these little cells in the universe out there somewhere that have memories in them. That's the kind of physics we're into now. You see this? They make it sound like it's almost certain. What if the universe remembers everything? A new theory rewrites the rules of physics. Yeah, it rewrites them all right. What if the universe remembers? A bold new framework proposes that space-time acts as a quantum memory. This is the kind of nonsense, and they won't look at the things right in front of their face that they can't help but see. And this has gone on for over 10 years. These are the particles that Fermilab found. These are the particles we found. This was like 10 or 12 years ago. I found these particles with Rod Warren. We found them in the experiments we did. They can't explain this, so they won't allow it to be seen. I'm blocked virtually everywhere, and I have the proof that shows the particles they've been looking for. And we found them, but we used light. We didn't use big atomic particles which just splash a whole bunch of stuff everywhere. And they call it a zoo because they can't find anything. We found it because we started with it. This is what they want to find. We found it. And they won't look because it's too much for physics. The same thing with the gigantic body parts. In geology, they just can't accept it. They just, don't show it to us. And that's been going on the same time frame, 12, 15 years. And what I am showing is you can't dispute this. And then there's the giant hearts and lungs and all these giant things. There's a guy standing there. In my stuff here, I have here, it's been DNA tested and CAT scan and everything else. We're living in a world of denial, absolute denial by the people we trusted to do the job. They sent a spacecraft out to this asteroid Bennu. It is a heart. When they came back with it, they came back with heart muscle. Here's what they came back with right here. Those are sarcomeres in muscle. That's a rope bundle of muscles. And this is what they brought back from asteroid. These are the membranes that coat above and below the sarcomeres so you can move like this. This is the sample they brought back. It has DNA, it has RNA, it has all the amino acids, it has everything that you can think of. That is all biology. And they grabbed it from a thing that is a heart right there. And Psyche is another heart that's out in space. That's a tube coming out of that heart. These are the valves. These are the colors of blood. All of it, and this is a second one. There was battles in the heaven. They cannot accept any of that. They hate God, they hate religion, they hate Jesus Christ, they hate anything that they can't explain that will take away from their status. And believe me, their status right now is in the toilet because they just can't live with the reality of what they found, which is heart sarcomeres. You want to see what a heart sarcomere looks like on Earth? Identical. These are heart sarcomeres from a heart attack patient. These are the phospholipid membranes above and below, and these are the blocks of sarcomeres. Not deniable. It's only dismissible, and they have dismissed me and reality and Velikovsky and everybody that won't say what they tell you to say. Now, I don't know how Feynman got away with it, but even Yale comes up and says, well, he doesn't know what he's talking about, and we don't know what we're talking about. Just tell everybody what we tell you to say, and you'll do fine. I'm serious. That's what they say. It's the first 1 minute of the quantum theory. Professor Shankar tells him at Yale, and he's right. It's true. It's just a tragedy that they have to repeat what he says. He doesn't know what he's talking about. He admits it. Okay, my friends, this is going to be kind of interesting. This goes back to 1964. This is Richard Feynman, one of the top physicists. And his claim was nobody understands quantum physics. Seriously, that's what he said. And they even repeat the same thing at Yale. I'll show you in a minute. But I was starting to take an interest. I was very young at that age. But in 1968, I went in the Army and I worked on nuclear Nike Hercules missiles, nuclear missiles, and the power generation and all that stuff to run that system. And I took a great interest in, and I pursued that for my whole life, and I went into electronics and so forth. Anyway, they didn't have a whole lot of nuclear missiles out in the, where you can go get a job. So anyway, I had a business, and it was an electronics business. Now, I was going back over this stuff. Now, he's talking about quantum mechanical view of nature, the quantum mechanical view of nature. Quantum means the smallest bits and pieces that make up everything. And now I'm seeing they're talking about having the universe have a memory. They're starting to fight back against my dipole electron flood theory. It solves everything. And now they're talking about the whole universe. Every little cell has a memory now. Because I've been showing the things in space are biological. They're not just rocks. And they have Bennu back here on Earth, which is a part of a heart. It has the muscle, it has the sarcomeres, it has the membranes, it has the DNA, the uracil, the RNA. It has all the biological chemistry of a heart, and it is a heart, and you can see it's a heart, and you can see the valves. And so is psyche. The whole universe, as far as I can determine, is biological, and all that stuff was talked about in the ancient texts. So don't come talking to me about having the whole universe have memory cells. Where do you see this? What's going on in science is staggering to my mind. To have them refuse to look at the things that I show that are material evidence and go off on these tangents about, I mean, it's really crazy stuff. And this is the article. What if the universe remembers everything? New theory rewrites the rules of physics. What if it remembers everything? How do you know it remembers everything? Show me something about that makes sense. You know, I don't want to be disrespectful, but this is it's just something built on nothing. A bold new framework proposes space-time acts as quantum memory. It's something built on nothing, and I can't even imagine why they would start to talk about this. But I do think this is a response to my actual physical evidence that I've been showing for over 10, 15 years almost, well, 12 years at least. And this is light accelerating. These are the particles of light, seen with CMOS. And these are the same particles they found at Fermilab and CERN. We actually have them. Now, this disrupts everything in physics. Yes, absolutely, 100%. So for them to come up and talk about disrupting physics with some new theory rewrites rules of physics, the universe remembers everything, I just can't even imagine what the thinking is anymore to evade this. If we're really looking for truth, somebody should have asked a question about this. I've had no questions whatsoever. I presented this to Fermilab. I had a big fight with Don Lincoln and Fermilab about this. And I ended up going to the University of Geneva online, and I explained to them what we did with light. They're using huge particles like this. We're using particles that are only one or two of these little particles. And they're using these. When they hit their CMOS, they destroyed it. That's why they said you can't use CMOS. I said, no, we're using light, so we can use CMOS. It's designed for light. And they decided, yes, I was right. And they ended up putting CMOS sensors in CERN because they're much more effective, and they don't have anything to do with interplay with the energies. There's no observer effect. You're just sitting back here getting popped by these little light particles. But for them, they could get hit by one of these and it would destroy the CMOS. We're never going to get hit by anything bigger than that. It doesn't destroy it. It just excites it. Then when they hit it with something like this, it's all over. And that's what they were using, is these big things, smashing them. We're using light. So anyway, this should have been examined for what it is actually the separation, which is fission and fusion of the light as it accelerates and explodes at the Venturi, and we can actually see the particles. All of this new way of looking at things, they're trying to figure some way of weaseling out of not understanding quantum, because the standard model doesn't work, absolutely 100%. Feynman said there's no possible way you can explain quantum physics with the standard model. And Yale says the same thing. All right, this is an article from 2013 about Feynman's issues with the standard model, and this is extremely deep. But the most important thing is right in the beginning, is that Feynman argued the standard model is inconsistent and incomplete. It doesn't work, basically. And he said that if you can't see it and experiment and show it, it's meaningless. If you just think something, you're just thinking it. If you can't demonstrate it, you can't make it work. Well, I'm thinking it, and then I'm demonstrating it. And here's where I was thinking it back when I was in college. I was deep into this stuff, and I actually ended up saying that the transfer of energy is from light into atomic vapor. And I showed that the Rutherford's atom was wrong. He was just wrong. And this is just a bunch of stuff, and this was my interpretation of energy, intermolecular forces. There's only two types: dipole, dipole. There's a polar and there's a nonpolar, but they're all dipoles. Molecular dipole moments. And then I went and I did some serious papers. I did as much as anybody in this field. This was 1970 or so, and this was some from the first light experiments. And I mean, I did everything. I did the chemistry. I did everything you could do in this to understand particles. I went through everybody's interpretation, Millikan's oil drop experiment, all those different things. And I came up with my own conclusion that everything was made of dipoles. And it's called dipole flood theory. That's right here. This is really what an atom looks like. And this is the smallest atomic unit, which is a proton. Now, smaller than that, which is one of these. And the black matter, the dark matter, is in the center, and literally is the dark matter. That's where the mass is, that they can't find because it's covered by all this white matter. You never can see inside to see the dark matter. You can't see it. Every time you look, you're going to hit one of these things because every bit of dark matter is surrounded by white matter, which bounces. You're never going to see that. It does not emit, it does not absorb, and it does not reflect. The only way you can see it is if it gets on top of the white matter that was coming at you. It blocks it. Yes, then you can see it, and that we have seen. Now this is a 5-minute read if you read slow. It's 1,839 of these dipoles make up one proton. A light particle is 2 of these. Each one of these is a magnet, back-to-back magnets basically. And these are the 2 particles that make up each one of those little magnets, is black and a white, electron and muon. And here they are. We separated these from their gluon status, and 2 of these back to back make up a photon. And there's going to be a few changes. That's it. That's the whole deal right there. You can understand this in minutes, and I can demonstrate it, not just say we did it. This is it right here. This is light coming forward. When it hit the Venturi, it exploded and separated the black from the white. And we could see the black, dark matter, because it obstructed the white. Not because you can see the black. You're never going to see it. The only way you can see it is if it obstructs the white that's behind it, trying to get to you. Okay, this is a whole ball of wax. This is actual experiments. A red pulsed laser coming through the air, being accelerated right now, just starting to accelerate and causing all these other particles in front of it to respond energetically, which makes them glow a little bit. It gives them a little bit of energy, and the CMOS can see that. Now, as this starts to accelerate down, because it's being attracted by this Venturi, it pulls itself right out of its own wave. This is the wave right here of magnetism, and it just pulls it right out of it. It's stunningly fast. It's just like breaking the speed of sound, only we're breaking the speed of light. So don't tell me you can't accelerate light or slow light down. Well, they know they can slow light down, but acceleration, no, that was never allowed. And you can see it's obviously done. These are real experiments. Now, the explosion here is so intense that all the other light particles, which you'd never see because they don't interact until they bang into something. Well, they're banging into something which is the reverse wave. And that's why all of the edges of them are lit up like candles. Just like this one is getting lit up because it's coming forward. This is a nuclear, subnuclear explosion. And coming out of the Venturi, looking into the Venturi this way, we would see this. These are the Higgs fields. And crazy enough is the Higgs fields are the same going in as they are coming out. This is going in. It looks like a Higgs field to me. It's a wave and a particle. The particle's inside the wave. The wave is all of the magnetism that surrounds the particle. So it has to make the wave, and then the particle is making that wave, so everything, you got a particle wave duality. So that's correct. But coming out the other side, right here, they got the same thing. Basically the same thing. Now, this is blue. Blue is very fast. You really can't tell much. But you can see it's coming in real fast and then slowing down here. This is the actual particles itself. That's what a photon is. And they're green, red, same thing. This one is the strangest of all, which I have figured out what happened there, which took me 3.5 years. All right, so these are the red. They just slower spin, and they spin. They don't flap like a wave up and down. They spin around in a circle as they go forward. This is as they're gaining energy. This is when they're in a full photon phase, and that's the only reason we can see this, because of the back splash from the Venturi explosion. These up here are also photons, but they never get to be the photon because they never hit a wall. Well, these hit a wall. They hit against their own selves back, so they think they just hit a wall. That's why that lit up just like a regular photon when it bangs off a wall. Now the green does the same thing. It was the same particle. All right, don't forget, this is the red. Now there's the green. And you notice how it's going in this direction, but they're still straight up and down spinning. They always go polarity towards the Earth. That's what they call upspin and downspin. And the white is getting charged up here, and it will flip to the back, and this white, this one will come to the front. That's called a muon wobble. They just go bloop, 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 and they spin as they go forward. But they're always polarized towards the Earth. And this is, this right here is the backsplash. We always called it our reverse EMF, electromotive force, electromotive push force. And this is pushing back. Electromotive force, electrons, motive, moving, force. What is it doing? It's creating a wave backwards. That's not supposed to happen. The wave is supposed to be going this way. Now, I started posting about this, and then all of a sudden I see online, well, we can see particles going backwards. That means time can be reversed. That's not going backwards. It's bouncing. That's all. This is a bounce back. It has nothing to do with time reversing. Every time I post something now, I'm seeing somebody is coming up with some nonsense that they're trying to keep themselves afloat. Why don't they look at what is real? This is reality. These here, all of those tiny little particles there, are gases in the air. They're picking up a little bit of a glow because they're being smacked one way or the other, this way or that way. And when you slap something, it glows. And when you explode something like this, it just goes off the charts. Now, you can see the black on top of the white. Let's get a little closer look at this. Don't forget, this is the pulse red laser. Zoom, zoom, zoom. And when it hits here at the Venturi, only the white is allowed through. Venturi is a slit, just like this. It's like the single slit or double slit experiment. You can use it, but you have to have it in a Venturi configuration. You can't just have it flat. You have to have it pulling all those waves together at the same time and getting through this little thing. And only the white can get through. The black is solid, and it's not capable of getting smaller. And that's exactly what Fermilab says. They said that's all the mass, and it never gets bigger or smaller, but it has the glowy edge around it, the black, And then they see this one, it can get big, it can get small, doesn't matter. And that's exactly what we found, those two same particles, the black with the glowy edge around it. You see it? This is right from Fermilab. That's Fermilab's picture, right off of their page. They say this one can get big, small, doesn't matter. This one, no matter how you look at it, it's always the same size. They're showing you, they've seen them in little bigger and bigger. They've only seen them because they're further and further away and different. I can show them that way too. I can show you bigger ones and smaller ones of this, but they're always just solid mass, and they agree with that. That's what this whole article was about, solid mass, and they say this has no mass to speak of, and it's just all energy. I do agree with that, and I can't account for that either, why it has no mass to speak of. I don't know if there's something there, but I would think there's got to be something. What creates the field? They don't know. I don't know either, so I'm not going to pretend I do know, because I don't. But it's some kind of a magnetic bounce. It's like a bubble that says, you know, I can get tiny, I can get big. I can flatten out, I can get big. And they do, they flatten out and go through the Venturi. All right, Feynman is as close to my theory as anybody has ever been. He understood about Diracs where nobody else did. Nobody did. And here's what he's talking about right here. And he was against all the other people. He was saying nobody can figure out quantum. It just doesn't work. So he says, first quantization bigot, Niels Bohr, who was a big shot, never understood how Diracs work. All right, in quantum field theory. It overturned Heisenberg's mythology, and he simply refused to listen to Feynman's second quantization proof, claiming it violated his dogmatic religion of uncertainty principle. They take a position and it never changes. So here's what Feynman was talking about, is Niels Bohr, he just didn't understand Diracs. Here's a Diracs. This is exactly what I show as our particles. These are the Diracs right here. You call them Dirac if you want. I call them dipole electrons because they're always two of them together. That's the smallest unit you'll ever find that's semi-stable. That turns into heat. It bonds with something. Electrons, they can get charged as static, but normally they will bond into something and cause heat. Now, two of them back to back make the photons. These are photons. And I showed this very, very clearly. And the dark matter is right on top here, which they called a muon. They didn't realize they found dark matter when they did these experiments. And that's the dark matter fusing back to the white electron showers. We didn't have to put it into heavy water. All they do is splash it in there and they see a bunch of things happen, lights flickering on and off, and they know there's electron showers. But I guess that's about it. Now we can actually see them and direct them where we want them to go. We can shoot these right where we want them to go. You see this? You just have to know how to tune the Venturi. Now I did all this stuff, and I actually went to, well, I didn't go there, but I went online to the University of Geneva for particle physics because I couldn't get anybody to listen. And they did listen to me, and we talked about this, and they did finally agree that CMOS was really the way to go to view the particles. Instead of using charge-coupled devices, they did actually convert CERN to using CMOS. They had to harden it because they were using too big of particles, destroy the CMOS. Anyway, I think I went over this before, or will. But this is the particle. And we're doing this very, very inexpensively, and we're creating exactly what they want to do, is to remove the white from the black and just harvest the white right there. We should be able to do that. I don't see any reason. Now, I've made this public for over 10 years, so there's no patents to use this type of technology. You can't say, oh, you can't do this because I have a patent. No, it's all free to anybody. But nobody seems to want to do it. I don't know why. I'm too old to get into this now. I'm just trying to figure out life, where I'm going after this one's done. And I'm telling you, everything there is made of these particles. And that was 1970. Transfer of energy from light is to atomic vapor. That's what light is right there. And it is atomic vapor. That's the smallest particles. And when it condenses, that vapor, it turns into a small stable unit, which is called a proton. And then protons get bigger and bigger and bigger, and more collect as these stable little units. It appears. These are like the building blocks. Now, I really can't tell you why they become stable at 1839 or 1840. 1840 would be a neutron. 1839 is a proton. Proton wants to either take one more on or attach to something else to use another particle's electron. And that's how you build molecules, is by the interaction of the outer orbital particles attaching to somebody else. You could come up and go bloop, and then one grabs on there, and then you got a molecule. But this one's got to want those, and this one's got to want to give them up, bloop, or vice versa. And they can get extremely entangled. And these are all the different points of stability, basically. But between each one of these is thousands and thousands and thousands of different particles that are almost like well, just take sulfur. Sulfur has a certain number of protons and then a certain number of neutrons. But you could have that sulfur have a whole batch of little particles missing. There's no problem. They still call it sulfur. But it's sulfur this, sulfur that, sulfur this, sulfur that. And it's the same sulfur, but it's got more particles, which are isotopes, or less particles, which they know of. And these are the half-lives that they break down to. That's what's called decay. So you have the sulfur, which is normally stable at, say, this is just made up numbers, 100 particles. And 100 of them together make it stable. Well, if you had 94, they'd still say it's sulfur. But it's drifting back downwards towards phosphates. All right, phosphorus. As it goes down, eventually it will hit phosphorus. It goes lower and lower and lower, it hits silicon. It goes lower, 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 it hits aluminum. That's the key to bigger and smaller. And that happens from enzymes. Enzymes do nucleophilic invasion and substitution. They work within the nucleus. Enzymes, very, very exotic. So now, I find this really funny, because I was, Rutherford, I had Rutherford's atom was wrong. If his atom was right, you'd have no light, because the predicted spectrum was black. If he was right, because of the way he treated the energy. Now, Feynman, apparently he hated them all too, because he said Bohr, he called him a bigot and all this stuff, and they're all tied to this dogmatic religion of this certain principle that they have, and they won't even look. They seriously will not look. I haven't had one single question from the people at Fermilab or anywhere. Even the University of Geneva, they tried to shut me down, but I didn't let that happen. And it worked out well for me, because they realized I was right. And if I'm not right, University of Geneva say Roger's telling stories that aren't true. They are true, and that's why I'm telling them. Now, here's Feynman against Bohr. Bohr said one could not talk about the trajectory of an electron in the atom because it was something not observable. Well, I just showed you it is observable now. Bohr thought that I didn't know the uncertainty principle, which means they can't really tell where it is at any point in time. It didn't make me angry, it just made me realize that they didn't know what I was talking about, and it was hopeless to try to explain it further. I gave up. I simply gave up. You can't talk to these people. Once they have an attitude, you're done. Feynman argued against the path integral being fundamental to particle physics. It always bothered me, according to the laws as we understand them today, it takes a computing machine, an infinite number of logical operations to figure out what goes on in no matter how tiny a region of space. Well, anyway, he was not happy, and people knew this. He was not quiet about it. He still got the Nobel Prize.